So thanks
Thanks
guys.
thanks for joining us, Jay.
Bye-bye.
See you.
Only give you a taste of the beginning of stuff, but yeah. So maybe I will start sharing. Okay, so couple of things. Recently, I found some book about behavioral types. Sorry, that's not this guy. This guy from 2017. That's something I've digged up yesterday. I don't know if it's interesting and relevant for what's happening in our train behavioral types.
It is based on some process calculus, or because you sent me some links and they're very closely related to pi calculus and behavioral types.
No, this is a bit different thing, but yeah, let's move to Statebox. So for me, Statebox is like interesting because they have plenty of videos about category theory that I'm interested in. This is a YouTube channel of one of the guys from the Statebox. They have some content related to blockchain. This is like a couple of vids. They organized conference when they talked about how category theory and Petri nets could be used to model different stuff, including different blockchain things. I'm mostly interested in category theory parts, but yeah. So they have a couple of things. They have library to encode category theory in Idris. It's pretty cool. They have some blog posts about this. They implemented this categorical query language in Haskell. So they have bindings for this in Haskell. That's cool also. And they are involved in also doing this guy, type devs. This is like language independent way to build data structures. That is cool also. But yeah, they've published, so they are responsible for publishing a couple of papers. This guy is the paper that I'm going through. But yeah, if you look up the authors of this paper, they have a couple of cool publications. Yeah, I love they are related to blockchain directly because yeah, lots of stuff about Petri nets. So yeah, you could take a look at what those guys are up to. Anyway, so yeah, that's the paper that I'm trying to understand with a couple of guys from my company. Yeah, because time is like not infinite. We are like beginning of the stuff. So as far as I know, they didn't publish this this language, this Statebox language. They want to get some visual language for easily defining stuff. They use Petri nets as a base model. They try to solve by this a couple of issues. It looks like you could model using Petri nets systems and don't get into the deadlocks. So that's super cool. Want to understand this stuff. Yeah, and lots of category theory things. So yeah.
Can you say something about Petri nets?
I'm like going into well, not meat, but interesting parts about this. So they have pretty readable. This paper is pretty easy to read. They define Petri nets. So it's a way to define process by separating inputs and outputs and modeling resources. So in here, the boxes are transitions. So this is like this models output of some process, and this guy, like this is like input of a process. So all this there are places as circles, transitions as rectangles, and there is this lines. So these lines show you how many resources you need. So for example, in here you need 3 resources from this guy to go into this transition. So that's the
so there is like a notion of linearity, or for like because you have resources to spend, right?
Yeah, you need to, well, in linear types, you are specifying that given resources could be used once, right? In here you are,
types?
sorry?
One or multiple types? Right?
I believe that maybe
I'm just trying to remember this talk from Benedict Party.
yeah, so I understand is that you want to use every type exactly, sorry, not type, every variable exactly once.
But he was saying that you can specify multiplicity. What
Then
does it mean,
you
multiplicity?
then your type is not linear.
Oh, I was thinking that you can specify how many times.
There is
multiplicity in that sense.
You know, I don't remember if you get multiplicity. I believe that there is something like quantitative type theory, and in there you can specify how many times given variable is used. But I don't know if it is implemented in this linear Haskell stuff extension. I don't remember, sorry.
Yeah.
But in here you have this like notion how many resources. So these dots, they are called tokens, indicate how many resources exist in given like state or something, and how many you need to move to the next, to the transition.
Oh, so this
like,
is somehow related to multisets, right? I somehow.
Yeah, so multisets are described a bit later. Yeah, so the important part is like to figure out if you can transition from one state to another. So yeah, and if there is no indication, that means that there is one resource needed. So in here there is one in this dot. So the tricky question is why this is not, why this transition cannot happen. And the guesses?
You don't have one to.
Yeah,
this.
in here. Because
you need to have one dot, right?
Right.
One dot to use it.
Right.
Okay.
So you cannot get one from this place because there's no tokens there. Yeah, there's a couple of, they mentioned that there are many different generalizations of Petri nets, but the way they use Petri nets allow them to have these nice properties like checking if there are deadlocks and stuff like that. So that's why they don't use some generalized theory. The multisets are cool because they are used to model two things in Petri nets. Yeah, and multisets or bugs. Yeah, there was I've linked a paper about boom hierarchy of data structures. So
you mentioned this last time, right?
Yeah. So multisets have these properties that they have unit, they have they are associative, commutative, but they are not. Yeah, that's all. The unit is like empty multiset. There's a bit formal definition of multisets, and they support only, they define operations in a particular way. By operations, I mean, they treat multisets as a functions. So it's a function that says how many times given element occurs. So this is
occurrences.
Yeah, and they deal only with finite sets or finite sets. There need to be finite number of elements that occurs more than once, more than 0 times. So yeah,
this is very related to rolling.
Yeah,
because when you have terms in a par, you're really putting them in a multiset, and this is the collection part that Greg was explaining. So you have terms like send in par with the receive, right? These are two terms with the par, constructed with the par. And how do you represent this in a collection? This is like a multiset. You have send and receive as elements of this multiset. So if you have two sends and receive, they can be the same. They are just element with two count in this multiset because they are the same. Okay. So we have this structural relation between expressions in the language. So when we parse the language, we just put all the terms in the multiset because the par is the monoid of operations on this language. I can show you the code.
Yeah, I get some different observation that petriness actually nicely fit into the calculus because you are modeling like receiving messages and sending messages independently. Like this is not very popular in type theory. You have function and that's all.
Yeah, exactly. Greg was explaining that in calculus you split application. So application is not one constructor. You split it in the send and receive.
Yeah.
But this is application. From one constructor, you are creating two constructors, send and receive. And application will be when you put these terms in a par.
Yeah.
When the names are the same and you are exchanging messages. So you have this reduction. As the same is lambda calculus. Application is the reduction.
Makes sense. You wanted to show something? I've stopped sharing.
I was playing with this code when Greg gave us like homework to do. So I did this. I think it's visible from one of the versions. This is just the definition. This is a representation, like an initial representation of rolling with like a concrete data type. Maybe I should not say concrete because it's abstract data type. But here is the par. So you have different terms like input, output, like send, receive. You can eval. This is creating a process, and par is constructor that put all the processes in the multiset. So if you have two terms that are the same, you will just have an element with count of two, with two elements.
But in here you can have like multiple elements, right? Multiple processes in this
Yeah, because
par.
this par is like a monoid for your language. You're combining the terms.
Yeah, I get it.
So and I'm not defining zero because multiset zero is is a unit. So I don't have to have a separate term constructor for zero. And if I show you the semantics, this is how it's created. Because I need to show you the final representation, like shallow embedding, where you have all of these terms. You have nil, you have par, you have input output, everything. And from this representation, from shallow representation, you are filling the data type. And this is what semantics is doing. And this is exactly from examples from Oleg Kiselev, how he is representing this semantics. This is how he calls this combination of syntax and semantics. He is defining this as semantics.
Nice. Yeah.
And you can see here when you have two pars. So when you have two pars in your language, when you're parsing the code, you're just taking these two terms and combining in the multiset. And that's it. So if you have par with par with par with par, you will put all these pars or all these terms in one multiset. So if you have two terms that are the same, you will just count it as two terms. So it's very simple when you think about it, you know, converting terms to a collection of terms. So you at the end you will just have one big multiset. That's it. The whole program will be multiset. And now you're starting to execute the reduction rules on this multiset, and you are executing the code.
Cool.
Yeah, that is totally cool.
Nice.
And this is why when you show me on this paper, you know, multisets, and I was, you know, wow, this is very similar.
Yeah.
But what Greg was saying, and what is difference with PyCalculus, and I think also with can be the case with patternets. Raw calculus have this additional thing that you can have the same language for the names. So for the keys, you can also have the whole language that you can use. You just quote your terms, and you get the keys for your elements can be like not only the simple names as in PyCalculus. And they also I think in the slides from these other guys that you mentioned, Pitts and Gabai, they're talking about naming nominal theory, and they are somewhere I found out that they are talking about more structure for names for PyCalculus, but I'm not sure if they have the whole reflection or they just have additional structure.
Sorry, can't help this there, because I just noticed that this is somehow related.
So when you try to do reduction, you have names. You have maybe it's better to look from data type. When you have input and output, what you really have is a key value map from names to processes, from names to processes.
Yeah.
So inside the multiset, you have these maps that you can, you have this key value store. So this name in row calculus can be any process that you are just quoting. This is like a reflection. You can go one way from you can go to names to the processes and back. So you can use the whole language for your names. You just quote it and use it as a name. And when you want to execute, you just evaluate it, and you keep your continuation going. So that's the main difference with the PyCalculus. You have very rich structure for names. Not only just a little. You have the whole language. You have everything.
Just not any theory of names, but
yeah. You don't need additional theory of names. So Greg was saying that Pitts and Gabay, they have very nice like this nominal theory and everything, but he was saying that they're using something little different than not little different, something completely different that is completely different than from this using it in Pitts and Gabay.
yeah, if I understand them correctly, they defined a new process calculi on top of PyCalculus. It's not like row calculus, something else. So yeah, and this calculi it has some nice properties, but I didn't understand what exactly are the properties.
You mean Pitts and Gabay? They're doing this addition another on top of PyCalculus.
Yeah, I'm talking about the exact talk I've linked into the chat. It was yesterday or something, or maybe earlier.
I was looking at something, but
where did I post it? Yeah. So I've linked program from this conference, FOPSS, and one paper. In this paper, they defined psi calculi.
This is very interesting. And they are defining bisimulation, big bisimulation, strong bisimulation.
Yeah.
This is something that Greg was explaining. Bisimulation and exactly this kind of relation. So I was reading exactly that. So let me go back.
They have some kind of different types of bisimulation, but it's above my head. Sorry.
Greg, I remember that Greg was explaining a strong bisimulation is exactly when you are, in lockstep with execution. So you are comparing two programs and they are completely the same. So their reduction rules are completely the same. But you can have a weak bisimulation where you don't have always the same steps, but from the outside perspective, you cannot see the difference between two programs. And they're explaining this as something that is they are the same from any context. So you cannot have a context where you can see the difference. So this is a bisimulation.
But they don't claim that they have strong bisimulation, right? They claim that they have weak bisimulation, I believe, at the end.
So from my perspective, it's very easy to have a strong bisimulation. You're just comparing all the reduction steps, and you're saying, okay, they are the same, so you have strong bisimulation. But when you have weak bisimulation, this is not completely clear, because with each reduction you lose something. You're erasing something. So how can you be sure that these two programs are the same? So you need kind of a rule to eliminate reduction steps, or to have some equivalence between reductions. So that's the problem. How to make an equivalence between reductions. So and why is this important? Greg was saying that Abramsky did this interpretation of linear logic, computational interpretation for linear logic, and he was using reduction rules to explain, or to he was using reduction rules to what? I'm not sure exactly.
Okay.
But this is the difference between defining these resources, this notion of resources, because so in Abramsky's representation, he was using reduction rules, just reduction rules to explain the how you manage resources, because this is what is in linearity about linear types.
Yeah.
He was and this other notion is not explained with reduction rules, but with some kind of other ways. And this is also like work from Philip Wadler. I'm not sure that I understand completely the difference, but I know that Greg was saying that Abramsky was about reductions, with reduction rules.
Okay. Do you remember what Philip Wadler work Greg was citing or referring to?
I'm not sure that I can recall now.
Okay.
I know Abramsky's work. Must be somewhere here. Oh, it's part of the logic, probably. Interpretation of computational interpretation of linear logic. Oh, it's on the first place. Oh yeah.
Yeah, that's why
Of course, this is important paper, you know.
Very cool.
I still didn't absorb the whole paper, but Greg was saying this is like a very important paper, so I suppose, you know, it's
I admire the amount of papers you have in your tabs.
you know, it's easily to collect everything, you know.
To read.
Yeah.
So maybe I will go back to Statebox paper.
Oh yeah. Sorry for this interruption.
No, that's very good interruption. Context is also always good. So yeah, I don't have like super much to add to this, but they define operations on multisets like union.
Intersection and union.
Yeah, and something like multiplication by scalar, similar to vectors. You just apply this, multiply this number with every number of occurrence in multisets for a given element. And they define this as like tricky notation, disjoint union. So disjoint union, you have like you tag elements from one set to different set. So if you have disjoint union for two sets, you can define the same stuff for multisets. And it's like the obvious way, you know, you count the occurrence from the one or from the other one. Yeah, there is this zero multiset. You can count all the occurrences, that's the cardinality. The injection is a bit tricky because you are using this empty multiset to like compose to union with any given multiset to like have this union. I don't know, it's important. Cool stuff is that multisets are free commutative monoids. That was new for me because I knew that lists are free monoids, right? And it actually makes sense because you could define using this boom hierarchy, also set would be like free bounded semilattice. That's something I've figured out. I never see something like that, like free bounded semilattice, but apparently it would make sense from this boom hierarchy data structure.
What exactly does it mean? I was a little. If you
free
remember, but if you remember from another party, Edward Met was saying about the lattice. So this is something that is like very shallow, and you have unit and connection to all the other elements, right? This is what this represents.
I have very bad memory, so I need to like okay, in here this would be like yeah, this corresponds to lists, so monoid is a free list. Multiset would be this guy, because we have this guy, identity and associativity. And the other thing is that we have also identity, idempotence. So this guy would be free. Multiset would be free bound semilattice. And bound semilattice is that. So, well, it's from the laws, right? But yeah, it have this empty element, some way to combine two elements, and it satisfies this laws. So identity, left and right, associativity, community, idempotence. Right? It's in Scala syntax, so it could be like.
Yeah, I'm trying to see what does it mean independent to x plus.
So
x plus,
you can
plus is this m append
operation.
Right?
So if you have one multiset, the set is idempotent. Oh, so it would not be a bound semilattice if you need idempotence, because yeah, but
you will have two elements, right? You will count, so it will not be the same.
I would have associativity, identity, and commutativity. Yeah, free commutative monoid. Sorry. This would be like set, because in multiset, if you combine two multisets, you would add elements. You would add in here. We'll count how many times it occurs in first, in the second, and add them. But in set, we just smash elements together, and that's it. They're only ones. Yeah. What else is worth mentioning in here? Yeah, but it was like crazy stuff when I saw this. Yeah, maybe I will not go there. 'Cause, yeah. And the multisets are used to define Petri nets in two places. I don't know where this is mentioned. Anyhow, you model
the number of resources is the number of elements, right? Exactly.
Yeah, there are two places where the multisets are used in defining Petri nets. I don't recall exactly when. So that's the story. I didn't get into like category theory part of this stuff. I'm trying to implement this, what I've already shown you in some programming language.
Oh, cool. Do you have something to show?
It could be Haskell. Currently, I've played around with multisets in Scala, but yeah, I would probably want to do this in Haskell. And I want to explore this reachability and deadlocks properties.
Reachability.
Yeah, I don't know if it is interesting for you guys. If you like to.
Yeah. Especially on top of this multiset, Greg was with the label algorithm. Greg was saying we will have modal logics between terms. So, and these logical operations are transformed to operations on the collection. So these intersections and unions, this will be translated from logical operators, from modal logical operators, diamond and box. So when you say, when you for example, he was giving us a simple Boolean logic. We didn't go too deep into the modal logic, but he was explaining Boolean logic. So you have two terms. And you can put logic in between them, in between. So you can say term A and term B. So you can combine send and receive and all the other stuff with the logical operators. And this is how you get behavioral types. And I think they also mentioned modal logics to model behavior.
I didn't went into that part, so sorry, I can't comment. But you are referring to Statebox paper or some?
I'm not sure. I was just
the conversation seems to be drifting a bit. Can I ask a question while I'm thinking about it, Peter?
Yeah, sure.
In the context of Statebox and category theory, I hear the concept open game talked about a lot. Do you know anything about that?
So I understand open games as a separate branch of math that you could use. And yeah, indeed, people in the recent Statebox meetup, or maybe in one of the videos, I've noticed that, or maybe there is a paper I've noticed, they combine somehow Petri nets with open games. I know that so there's, I know if open games are like the same stuff like game semantics, but game semantic is different way to express. You can model concurrency in game semantics. I know probably nothing more about this stuff. I would like to.
But no, thank you. That gets me further down, and that's what I was thinking. It was some sort of area of mathematics, and so I'm gonna do some searches on it based on that. When I put open games on on Google, it you know it got I got nothing helpful. But I'll frame it in a mathematical way, and I bet I'll get some hits.
Is this part of the game theory or?
Yeah, one reference I saw suggested it was tied to mathematical game theory. So yeah, that's probably a good lead.
So there was, there was session types and game semantics. This is a paper from 2019 and talk at ICFP or something like that.
Can you
So
post the link?
Yeah, can you share the link or just show me the link and I'll find it.
Maybe
show
you
me
can
your
post it on
screen.
Discord.
I can post to the chat on the Discord. So that's the paper. I've tried to watch it. I didn't understand too much. And about open games, I believe one of the guys from the State Box have some like paper or something. I'm trying to.
Oh, this paper is from Nabuko Yoshida. I think Greg was talking about she and this paper from Mike Mike and Greg. They were implementing what?
Oh, so you're referring to row combinator, R-Chime cast, or this paper by Greg and Mike Stay, right? About
About Yoshida's. They implemented Yoshida's combinators without external theory of names. Yeah, that's right.
Yeah. So I don't have too much to add. I've noticed some papers about open games and Petrinets, I believe, but where I don't remember. If I get to this, I will post it. Anyway, like everything seems to connect it to everything. It's hard to
we are much closer to these behavioral types and from different angles and
Okay, so that's all I have about Petrinets and Statebox.
Cool,
maybe it was like in one of the videos. I will try to find out where I get this open games stuff.
Thank you. I appreciate it, but this has been helpful.
We started out with the expression problem.
Sorry?
How does that relate?
I believe it's not related.
Yeah.
So I believe expression problem is something that attacks programmers because they can have only flexibility only in one way, either to add different like subtypes or different operations, and you cannot get both. And there are a couple of solutions, and I believe that type classes are one of these. So Haskell has some story for expression problem, and I believe also scheme or closure have something like multi-protocols or something like that, and this was supposed to be also a solution for expression problem. But
is this problem is related to some kind of mixings that you are creating? And
I don't think so. They have like some syntax for this multiple protocols. I didn't investigate this very much.
I guess a relation would be that the expression problem must be addressed in order to define behavioral types.
Yeah, I was also thinking that it is programming, like a programming problem, but what is the programming problem? It's somehow related to mathematics and some kind of deeper, much deeper problematics. Or because when you're doing when you creating implementation for something, you're really writing proofs, right? So you will have this problem, this expression problem, one way or the other, somehow.
Will hit you, yeah. Okay, so do you think that stuff that Statebox people are doing is relevant to like our training?
Yeah, I was definitely drawn to Statebox when I heard the first time. I think you mentioned when we were talking about we were talking about in Poznan.
Yeah.
I'm not sure who first told me about Statebox. So I think it's you. So I'm not sure.
I'm like Statebox and well, there's not many companies that use seriously math to like drive their business, and Statebox really believe that category theory is like answering the right answer for problems that people have in programming. So they invest into encoding category theory and expressing, building libraries based on math. That's their story, I believe. And they have
what is math?
Mathematics, sorry.
Oh, okay, so.
So, for example, this type defs is based on initial semantics. So initial algebras from the paper or from this presentation by Professor Neil Gani. This was explained before the vibration in this paper. Yeah,
this is related to index types, right? Because and this is related to Greg's talks about rewriting the derivatives, right?
I didn't digest that.
You have this kind of you're not talking about types as Connor was you sent me this repo from Connor when he was explaining. He had a notion of one type, two type, three type. How many parameters your constructor is receiving.
Yeah.
So this is how you calculate the type. So you have ID which accepts only one, but you can have like unit which is like a one type, and this whole hierarchy is like it can be indexed by the number of constructors, and this was like almost the same what Greg was explaining for his notion of types, but he doesn't call this index types. He has another like explanation.
Okay. I need to go in a second, so yeah, thank you very much for the conversation. I will try to dig up into.
Can I ask one more a question?
Sure.
Quick. I'm going to ask it by sharing the screen. I went to the Wikipedia article on the expression problem.
Yeah.
And I'm trying to read it. And I got down here. And I can't, right here, they talk about the discussion that led to it. And I don't understand what this means right here. What is PLT?
Programming language theory. So theoretical knowledge about computations.
Okay, so that I'm expected to know that. Okay, for PLT, the problem had shown up in the construction of doctor scheme, now doctor, and they solved it via a rediscovery of mixins. That Thomas Slav, is that what you were talking about?
Yeah, I was not talking about exactly that. This was my just notion that, you know, at the end, when you're combining these effects, you're really creating something like mixing. But yeah, I didn't know that they are calling this mixing.
Okay.
Yeah.
All right. Well, that's thank you. That helps, and I'll continue reading that article now. And I figured this would be the group to ask about it, since that's where we started talking about.
I could also explain this acronym badly, because they were talking about scheme. So there is two PLT scheme, as the dialect of scheme. So Dr. Racket is like newer version of PLT scheme, or dialect of PLT scheme. I could get this wrong, but
Yeah, I have used both of those, Peter, so I'm familiar with what they're talking about. Yeah. And you're right. Scheme came first, and then Dr. Scheme, and then Dr. Racket. Yeah.
Yeah.
And then this guy, Srinam Krishnamurti, he was he had a very nice explanation of the Dr. Racket, and like the course is about programming languages. For me, this was like super useful.
Yeah, I know.
I can share the link.
I know what you're talking about, but it's called SICP, SICP. What is it? Structure and Interpretation of Computing Languages, SICP.
Yeah.
SICP. Yeah, I'll type it in the channel.
Yeah, I know this book.
SICP.
Oh, but I was referring to lectures.
Yeah. But there's a sequence of videos about, by the authors of that textbook, which are fantastic. Yeah, I highly recommend them. And they're called the SICP lectures.
Oh, really? I was not aware of that.
Yeah, the textbook and the lectures actually go together. But I'm like you. I saw the lectures first before I ever discovered the textbook.
So here are the lectures. If maybe you can see if this is the thing. Let me add some title.
It should be at MIT, right?
No, it's CSCI. Introduction to Programming Languages.
No.
No. I posted in the Discord.
It's a very famous book.
By Krishnamurti.
No,
by Abelson and Sussman.
Yeah. Here it is.
Oh, okay.
I want to show this book because this is what I believe they're talking about.
Maybe I'm referring to different thing.
But the videos that go the videos that go with this, and I believe it's Sussman that does the videos. The videos are fantastic.
Yeah.
Oh, we are not talking about the same thing. This was exactly from this guy, Srinam Krishnamurti. So, yeah, we're not talking about the same thing.
Somehow, people nowadays tend to use Dr. Racket for designing languages. I believe something in Idris 2 was done in Dr. Racket, but I don't know why. What's the story? There was some talks about this recently, but I don't know exactly what's so super cool about Dr. Racket that people use it for model.
Yeah, I heard the story of the jump from Scheme to Dr. Racket, but and I ended up using both of them because somebody was doing something in Scheme that I wanted to see, and then I ended up somebody else was doing something in Dr. Racket that I wanted to see, and so, you know, what I was gaining from it was you know, I knew it was the same basic language. Yeah, the extensible language, and to me, that's I just translate all that into Lisp and then go with it. You know, I mean, I think in terms of Lisp. Yeah, and I would never use it for anything other than to play with concepts. I don't see how you would develop much in there useful, other than for demonstration purposes.
Well, to me, it looks that you can very easily create some kind of domain-specific language, and then you can program in this higher level language. This was, I think, a lot of the work of this Falstein guy, who was working on Dr. Eckert. I seen it in your screen on one paper. He was like he's a very famous guy. Where is Matthias Falstein, I think. And he has very interesting site.
You are sharing something?
I put it on the Discord. You have a warning on the homepage. And so on his personal site, on homepage you see different phrases.
Oh, I didn't get this guy. Anyway, I need to go. Thank you very much, guys, for
Thanks, Peter.
conversation. Yeah.
Thank you. This was very interesting.
Yeah,
I still.
Yeah.
I still not sure I understand what state box is, but I feel that all this discussion is going to lead me to an understanding of it.
Is that necessarily tied to Petri nets?
Yeah.
Okay.
I've got one last request. Tomislav, that PDF file that you had on your computer earlier regarded row. I remember the screen said binding names. Could you copy and paste that link to that PDF in the chat?
Yeah, I get this link from Peter. So yeah, I will definitely post the link.
Okay, I appreciate that.
Yeah.
Right.
Okay. See you.
Thank you,
Bye-bye.
everybody.